Okay, we're going to have a bit more fun with our lights. You can even add another couple of LEDs if you want. And I'm going to challenge you to write your own code this time. Now, I'll introduce you to two new instructions and how to use them, give you a couple of tips and some code cheat sheets, but I'll leave it up to you to write the program yourself. Now, you remember the KITT car from Knight Rider? The light in the front would go, back and forth. We're going to do that with LEDs. And in fact, let's up the ante a little bit. And I'm going to challenge you to make various patterns. Now, Jake Wolf on YouTube demonstrates here some of the patterns he has on his car. So remember, you have the entire pick instruction set, complete with how each instruction works, in your data sheet for your pick. Now, you feel free to attack this any way you like, but I'll introduce you to two new instructions from the instruction set. LSLF for logical shift left, and LSRF for logical right shift. So let's say I have a file or register and it's got this binary number in it. I send the LSLF instruction, which is a logical shift left on a file. It takes every bit in the register and shifts it left 1 bit. It puts a 0 in the least significant bit, and the bit coming out the other end gets shoved onto a special single bit register called the carry register. We use that register for math operations, and we'll address that in more detail later on. So you can see how this instruction could be useful for our KITT car light. Load latch C up with all zeros except for a 1 on the least significant bit. You have up to 6 pins, so let's hook up an LED to all 6 pins. I can now shift the register left, and every time I shift it left, it turns off the current LED and lights up the next LED in sequence. Now this is great until we get to the end, because now we got to go to the other direction. Not a problem. We issue a LSRF instruction, logical shift right on a file. It does the exact same thing LSLF does, only in the opposite direction. It loads a 0 into the most significant bit, shifts all bits into the register 1 bit to the right, and the least significant bit goes into the carry register. Now, we don't care about the carry register in this case because we're not doing any math. So the instruction to shift left would look like this. We have the instruction to perform a logical shift left on a file. Then we tell it which file on which we want to perform the shift. And then there's that destination number again. This is one of those ever so powerful multiple step instructions where once it performs the logical shift, we can put the resulting number either into the working register or right back into the file from which it came. A 1 there means we put the result right back into the latch C register. Logical shift right follows the same format, exact same format. Okay, so that's one way you can make the KITT car light work. You could also just make a series of steps where you load the working register with the number you want, then transfer the working register to LATC like this. So as it runs through the program, you have just manually told it what output you want. You have manually programmed the light pattern. This has one advantage in that you can simply program very complex patterns because you're putting your incredibly well-designed supercomputer to work instead of the pick. So you could easily make a pattern of multiple lights going in 2 different sequences, for example. The advantage of using the logical shift instruction is that you can put it in a loop with a bit test. So in the space of, say, 4 instructions, you could keep shifting left until your bit test sees that the highest bit is now high. Now, in our case, we've only got those 4 LEDs. So bit 3 is the highest bit with an LED. It can then leave that loop and send it to the loop shifting right. When bit 0 goes high, it then goes back to the loop shifting left. So if you had a 16-bit register with 16 different LEDs hooked up to it, then obviously this would be a simpler way to go. So as you can already start to see, there's a bunch of different ways you can do this, and they are all correct. They all work. Now remember though, the clock is running at 16 million cycles per second. So even if you give each instruction an average of 8 clock cycles to finish their job, that's still 2 million instructions per second. Obviously, you need to put delays in there, otherwise it'll just look like the LEDs are on constantly. You have now accessed the general purpose RAM, the GPRs. So you can make use of that and set up a countdown loop like what we did with the debouncing program. But we can only store a 1-byte number in our RAM. So that means we can only count down from 255 to 0. Now, do a bit of rough math here. At an average of 2 million instructions per second, that's 1 divided by 2 millionth of a second, or 0.000005 seconds per instruction. So for it to count down from 255, it'll take it 0.0001275 seconds. That's not much of a delay now, is it? So you need to double up on your counts. If we set up 2 registers with a decimal number of 255 and count down from 255 to 0 255 times, then 255 times 255 times 0.000005 seconds equals 0.0325 seconds. So now the delay is getting long enough that your eye could see it, but it's still really fast. So we have this sort of canned delay loop in the sample code. You can copy and paste and use this if you want, and I already figured out the timing. So you remember back in our very first PICT program, we saw that the number of clock cycles needed to perform a function can radically change from function to function, right? Some steps only took 1 or 2 clock cycles, others took 8. I actually set up and timed the program to get a handle on timing, and it worked out to about 6 clock cycles per instruction in my program. So this canned delay loop took about 0.05 seconds to run. Now, I'll go over it though, it's actually pretty simple. I've set it up as a subroutine with the return at the end. We first load up the first and second general purpose RAM locations with 255. We then set up a loop within the loop, count down 255 times on RAM number 1. When we hit 0, we count down on the second RAM. Then go back up and count down from 255 again on the first RAM. We keep doing this until the second RAM also reaches 0, at which point we simply return back to wherever you called the subroutine. So now if we used a third register, we can simply call that canned delay loop as many times as we need to get the delay we want. Every time we call that canned delay loop, we get a 0.05 second delay. That third RAM register is also a single byte, so we can count up to 255 times. And at 0.05 seconds per call, we can delay up to 12.75 seconds before we need to get a fourth RAM involved in counting down. So let's take a look at a sample code, assuming that we've already set everything up and our LEDs are on port C. So we then set up a main loop, then set all of the latch C to all highs so that all of the LEDs are on. We then load up our third RAM location, RAM register, hex address 072, with a count of decimal 10. This sets up how many times we call the utility delay subroutine. And at 0.05 seconds every time we call it, That gives us about a 0.5 second pause. So after setting up a label, marking the start of where we hold the LEDs on, we then call the utility delay. Utility delay subroutine, which is way down here at the bottom. It ties up the processor for about 0.05 seconds and sends it back to us. We count down 1 on the third RAM and then go back to the label delay on. We then go back to the utility delay for another 0.05 seconds, come back, count down 1, and do it again. We keep doing this until our third RAM hits 0. We then turn off all of the LEDs on port C. We reload our third RAM location with a value of 10, and then cycle through delay calls for the utility delay. We then send the program to the start of the main loop, turning on the LEDs and counting down again. Does that make sense? So you can actually throw this code into a project and flash your PIC with it if you like. And if you're really brave, replace the third RAM register with a variable so you can simply and easily change the timing of the flashing by changing one number. So now it is your time to shine. I'll give you some common mistakes or problems you'll run into when you're trying to write your program, as well as some tips. Before you try to flash your PIC, save your project. Second, build your program first, then, if the build is successful, then flash your PIC. It can hang MPLAB if you try to flash your PIC and the compiling fails because of an error. And you're going to get a lot of errors. That's just part of programming. Don't be too hard on yourself. Now, for starters, go ahead and copy and paste the setup code into your program. That'll get you started. And as you're programming, notice that it recognizes commands. It turns them dark blue. Let's say I made a typo. Move WL instead of LW. Notice it turns purple. It doesn't recognize it as a command, so it assumes it's a variable of some kind. Variable's in purple. So double check it. Something's messed up there. Labels are black. And when you need to make a label, you need that colon at the end. But when you send the program to a label, either with the goto command or a call command, there is no colon at the end of that label name. So remember, the only lines that should be in column 1, the far left, should be labels. Everything else must be indented at least 1 space. Otherwise, you'll get an error when you build it, and it will tell you what the offending line was, and it will probably tell you it found a command when it was expecting a label. All comments should turn green. If it's not green, you forgot the semicolon at the beginning of the comment. One of the most common errors you will get is label not defined. It will tell you what line and what label it went looking for. There's several reasons this can happen. One, you put your subroutine or label after the end command. Or you misspelled either the label or the name of the label where you made a call or go to. Did you use a capital somewhere? Did you accidentally type 2 letters in a row in the name? Or 3, you just plain forgot to make a label. 4, if you forgot the colon at the end of the label. 5, if you forgot to declare a variable, but you used a variable in your program. This can happen if you write it in a command somewhere. And you intend to put the declaration in later on, and then you just plain forgot. Another common mistake which can cause all kinds of weirdness is you forget to select a bank. Whenever you make any command that involves changing a register, throw in the bank select command, just to be sure. It'll save you a lot of hair pulling and grief. Trust me on this one. I did exactly that when I was writing this lesson, and it took me forever to figure out why my program wasn't working. Your program needs to have an end command, but make sure it's at the end. If you do like I tried to do a couple of times, and you put your subroutine, after the command, the compiler will spit out weird errors about how you didn't define a label. The truth is, it's looking for a label after the end command. But when the compiler sees that end command, it assumes it's the end of the program. So one last thing, which is actually not that common a mistake, but can happen, you get a stack overflow or a stack underflow. The most common occurrence of a stack overflow is when you call your subroutine, but then you goof, and instead of putting a return at the end of the subroutine, you put a goto. So it goes back up here and does everything again, getting a call to the subroutine. Eventually you overflow the stack because you have too many calls and not enough returns. A stack underflow most often happens like this. There's nothing here sending me back to the beginning. So once it's gone through the loop, it continues on, goes through the timing loop, then sees a return command. It never got a call command, so the stack is actually empty. So when it sees the return command, you get a stack underflow condition. Too many returns, not enough calls. So as you build your code, look at the errors. It'll often tell you exactly what the error is, and sometimes even how to fix it. All right, I'll let you attack the program. If it works, hey, share a video in the questions or comments sections. Show us what you did. If it doesn't work and you just can't figure it out, post your code in the questions section, what you're trying to do and what it's doing. Another set of eyes can sometimes make a huge difference.